5, so you have time to eat. And the lecture today is on das System Stadtentwurf, the city as a system design. So we want to focus on the interrelationship between the city as a system and design. Design of a city is something quite complex, as you can imagine. Many people say it is not possible to design a city, and we want to approach this difficult problem from, again, the stocks and flows approach that we started last week. And I want to give you one particular example I want to focus on in length today that shows you the relation between energy, noise, and other stocks and flows and design, and what we can learn from it in order to design a city or to improve a city. So we are here now on the 7th lecture, and going back to our big map, we are on the medium scale, the city as a system block, if you want. And today we will focus on space and on energy and how they relate to design. At the end of the lecture, we will look into another way to approach design, system design, city as a system design, and you will hopefully make the connections between what you heard before. I want to refer to the work I'm doing together with my colleague, Dr. Matthias Berger, from the simulation platform in Singapore. And our goal, after observing the city as it works and studying the city as it works, is exactly what you see in this title: Cooler, Calmer Singapore. But let me give you the reasons for that. Over the last 35 years, in that city, by the way, the same applies for a city like Zurich or Basel, there is rising temperature. You can argue where that comes from, but it's a fact. There's increasing noise. There's more flooding, sudden downpour, sudden flooding that cannot be predicted, and increasing density. So these are phenomena that we share in many cities of the world, and therefore they are worth studying. Is any one of you from a city where the temperature is going down? Are you aware of that? In your city, is the temperature going down? Seems not to be. Any city where the noise is going down? No. Maybe if you were in cities that are actually shrinking, then the noise could go down, the temperature could go down. Flooding, maybe that is not so relevant for you. Anyone in a city whose density is going down? No. So actually it looks quite relevant. And all these factors here, they influence design. Or if you turn it around, if we do design of new cities or improve existing cities, we have to take these factors into account. I want to start with a map of Singapore, because Singapore is a city-state, an island city that was designed almost from scratch. And I want you to look at this map and guess where is the city center. These are just temperatures. At 10 p.m. in the evening, June 13th, 2012. So where would you guess is the city center? Well, you know. No. Where's our guest from Singapore? He's not here today. Make a wild guess. We have really good distribution of temperatures. Here it's 30.4, 30.3, 31.2, 29, 26, Any idea? Make a guess.
Where it's hottest, 30.8 on the left-hand side.
Over here?
Yeah,
30.8?
around there.
Yeah, actually that's pretty close, but not quite. Anyway, later we will see this here is an industrial part, so that can be quite hot. Actually, it's in this area. Is the original downtown. And what about this one, 26.3? What could that be?
It's a park.
It's a park.
Yeah,
Yeah, that's true. So imagine, in the beginning, the whole island of Singapore was really a jungle. And the temperature was really even lower than that one in the entire jungle. All the rest has been changed, has completely been built up. And so that change, we are convinced, or we can prove with evidence, is man-made or human-made. So that design of the city has changed the temperature completely. This is the next morning, 7 a.m. Normally, in most of the places where you come from, overnight the temperature goes down, right? And in the morning it's nice and fresh and cool. Look at the temperatures here. That's 7 o'clock in the morning. It has not changed very much, just very, very, very little. And we see still the hot parts here. And we still see in the middle it's still cool. So this is like an indicator how human interaction, human planning has changed the island, and that with the city design also the environment has been changed. Here we come now to some hard numbers. This is measured in a place, Paya-Lebar, which is an old airport somewhere here in this part of the island. And normally at airports you always measure the temperatures quite exactly. And the airport is quite old, already from the Second World War, but the measurements starting here in 1955 show the temperature, normal temperature, 26, 26.2, 6, 9, around 26 degrees. Then there is a gap between 1980 and 2000, and you can see it is much higher after 2000. So 20 years gap in between, and something happened in these 20 years. Now, those of you who know the history, and of course, if you think of a city, designing a city, improving a city, you always have to know the history. This is like the stocks and flows of time. And between 1965, when the city-state of Singapore was founded, which would be somewhere here, and when the industrialization started, it's going up and up and up and up. And then, of course, industrialization between 1980 and 2000 was really, really very strong. Here is the same, but on a different scale and in a different representation. We thought there might be an anomaly of Singapore temperatures because people complained it's so hot. And it's getting hotter and hotter. Old people told us it used to be much cooler in earlier days. And we didn't know why. So this is actually how the whole thing started. So it was the people telling us it's getting hotter and hotter. We don't know where it's coming from. And we started to look. We did a comparison of all the temperatures that you can see here around the equator. So what you see in the green line is the temperatures around the equator in this area over the years. So it starts from 1955, the same time period again, and goes all the way to 2012, 2013. And indeed, the temperature around the equator is slowly going up. This is, some people attribute it to global warming, to other factors, whatever it is. And also this other line, the blue one, this one, and the red one here, is measured temperature north and south of the equator. Quite a strip of land north and south of the equator. So indeed the temperature is going up slowly around the equator. But if you look at Singapore, and this is this line here, there you have very different developments. How can that be that in the same vicinity of the equator you have such differences? And that brought us to the idea there must be possibly something that has to do with the development of the city. So that's the temperature. How about the noise? Do you know what is the noise level in this room now, if I don't speak? What do you think? How many dBA? Yeah?
30?
30?
Yeah.
That would be very, very low, but
Yeah.
it's close to, it's between 30 and 40, close to 40 probably, if everything is quiet. So this is where you can work quite well. You see those numbers? Above 55, it starts to be annoying. And above 65, it starts to have adverse health effects. And all the design that we do in cities, of course, has to take this into account. If you remember how people were upset or are upset by the so-called Anflugschneisen of airplanes coming into the city, because it raises the noise level at certain times of the night or the day, and how that even contributes to the degradation of the land value or the house value, you can see how important noise is in our society here. These are the buildings where people live in, the so-called HDB, Housing Development Board buildings. These are buildings that can be between 6, 12, 24, 48, 60 floors high. And here students from Singapore measured the noise level of different places. Clementi is a road close to the center of the city. Sengkang block is also closed, and West Coast is on the western side of Singapore. But it's relatively clear that on Clementi the noise level is quite high. Interestingly enough, not only on the first floor, this would be the first floor, the second floor, the mid floor, the higher floor, it's always very high. How can that be? And the same for this one in the center, a bit less loud in the west. There the density is also less. But definitely it's something you don't want to have. When you do design, you don't want to design that you're sitting, the same noise level is like if you're sitting in a car which is going at, I don't know, 100, 120 kilometers all the time. So that is just quite a lot. The third point is so-called downpours. Here we don't have these downpours, but in the tropics, of course, you have sudden downpours, but normally they come quite steady. In some places, increasingly in cities, they become completely unpredictable. They suddenly occur. And then you have lots of rain coming down, so this is more than 40 millimeters per hour coming down suddenly. And you can see the frequency of these sudden downpours has also increased between 1980 and 2010 by more than 30%. And so our goal was to look at this because people were complaining about this. Citizens were complaining about this. So they complained about the temperature, the noise, the flooding. And the goal, of course, is to see, is it possible to reduce the noise, to lower the temperature, to reduce the flooding, and thus increase the quality of life? Again, always think, this refers not only to a tropical city, but to any city. And if you do design of a city, or try to improve a city, the biggest impact you have in improving those factors is through design and through knowing the interrelations of these things from the very beginning. This brings us back to our old theme, the stocks and flows, because you can think of the stocks and flows related to temperature, would be, of course, energy. Stocks and flows to noise, you can also trace it back to energy. Flooding, that is also most likely connected to the stocks and flows of energy release in a city, around the city. And the quality of life, of course, is what you want to have for a city. This is your present exercise, if you think about it. The quality of life, think of what really gives the city that you like most its quality. And for that reason, that so much of those factors are related to energy, we had to look at the heat flux in the city. And the heat flux is something different than just energy, it's something different than just temperature. We have the contributions to heat flux in Singapore from industry, very high, from transportation, quite high, from buildings, moderate, and the most important one, we think, is through urban design decisions and urban planning decisions. Now, how could that be? We have to revisit two charts that I showed last time and look at them a bit more in detail. For that, we make a comparison of the energy landscape in Switzerland and Singapore. If you remember the so-called Sankey diagrams here, the Swiss Federal Office of Energy releases those numbers every year. They are very important and they are very precise. And you can use them then to make visualizations like that. So if you remember from last time, we have on the left side the energy supply that comes into a country. On the right side, the energy demand, which is how this energy is used. And of course, you see between supply and demand, there is the transformation, because you can never lose energy, it's just transformed. And as I showed last time, in Switzerland we have a very varied, a very diversified sources of energy supply. So you would have crude oil, petroleum, natural gas, nuclear power, and water. And you would see how many petajoules, this is the number in petajoules at the top, is delivered in terms of supply. Then you have the transformation, and you can see the transformation losses. For example, here 13,615 petajoules that go out from the transformation of crude oil into petroleum that are lost, if you want. They don't get lost, they just get up in the air or into the rivers or somewhere, and they contribute to the heat. Or here from nuclear power, you know, these big nuclear power cooling towers, and you can see 186,000 of the 278,000 are being released as heat. And the usable electricity is this proportion here. Whereas from water, if you have this water supply here from the glaciers, from the river and so on, the losses in transformation to electricity are very, very, very small. So this is a very interesting view of the energy supply. Of the transformation, you can see all the ins and outs. These are sales to other countries. There's imports from other countries coming in, electricity coming in, let's say from Austria, from Germany, from France, electricity going out, being sold to Italy mainly, and so on. And then you can see the total bulk of electricity, how it is then used, just as an example. The electricity is then used or demanded in buildings, which is at the top. These are residential buildings, so they demand electricity for lighting, for these kind of things, some for heating, for hot water, and so on. But they also require natural gas. You can see the natural gas is going into these residential buildings, and they require still a lot of petroleum. The old buildings that are oil heated, so they go into these residential buildings. And you see that 27% of the total energy demand is just by residential buildings. And as we know, in Switzerland, it's quite cool climate, so most of this is going into heating. Like today, this building, the majority of the energy needed is going into heating. So you can go through this for every single part, and you observe industry is quite low. It's 19%, which is amazing because Switzerland is one of the countries with the highest industrial output per person in the world. So how can that be? With so little energy, so much industrial output. It must be pretty efficient factories or very smart output. So then this is commercial. And you can see it's 15% commercial. And this one, the biggest part, is actually the transportation. And you can see the majority, the absolute majority, is gasoline, diesel coming from these sources up here, okay? Going straight into transportation. And you can see a tiny bit of blue. Actually, this is good because only on this display you will see that. If you have a lower resolution display, you won't even see that little line of thing. This is the electricity for all your trains and trams and stuff. Okay, this is quite amazing how small that is, and very, very little natural gas. So the majority is really is just gasoline. And you can see the primary energy supply is very diversified in these colors here. Remember that. And opposite to that is Singapore. And you have, as I said last time, only two sources. The one is crude oil, this one here, and the other one is natural gas. And the natural gas is converted in big natural gas plants into electricity. And you can see in comes 194,000 petajoule. There's a loss, whatever, of 99,000, almost 100,000, and out comes 151,000 petajoule of electricity going out. Then this electricity, like in Switzerland, is going into the housing, into the factories, in the production, into the commercial, the shopping centers and all of this, and into transportation. This is a bit more because there's a lot of subways, MRTs, as they are called, that are used for that. And that means they have only two sources, and unfortunately, both of these sources are carbon-based. That means they produce, in their transformation, heat and carbon dioxide. And that means the entire energy is, in the end, converted into heat. Only 5% go into buildings. Look at Switzerland, 27% in residential buildings. 60%, almost 60% go into industry. Before, only 19%. 11% goes into commercial, 15% in Switzerland. And only 21% goes into transportation, in Switzerland, 36%. The interesting part now is, if you look at the total demand at the top, 852 petajoule. What is the population of Switzerland? How many?
8 million.
That means how many per person? Anyway, maybe it's easier this way. If you look at the population of Singapore, look at the total demand. So the demand per person in Singapore and Switzerland is identical, but it's different distributed. Why do I talk so much about this? Because it is energy eventually turned into heat and released in the place where it is used. Transformed into heat and released in the place where it is used. And if we look at the Swiss landscape, Switzerland is always saying it's a small country without natural resources. Singapore is saying exactly the same thing. But if you look at this lake here, this one, Lake Geneva, that is almost the size of Singapore. Because originally Singapore had an area of 450 square kilometers. It was added land. So Singapore is really not much bigger than this Lake of Geneva. But if you imagine that you put 531,000 terajoule onto or into Lake Geneva, I think you can imagine something will happen there. because the total energy demand for Switzerland is 852,000. So there is a huge energy density that you would add into that lake. To explain it a little bit more, everybody knows this one, coming back to architecture. Important event in Switzerland, in Zurich, is this guy there on the left side. Who of the people not from Zurich have seen that, what happens with this poor guy there already? Yeah, just 1, 2, 3. Okay, so what's happening is this. So this is before, and this is after. So this is the end of the winter, as it's called, and this is the so-called Böck, and the Böck is being burned, and when the head explodes, that supposedly shows you how good or how bad the summer will be. But it is interesting for us because it's burning energy that results directly into ambient heat. And this is the formula that you might remember from your physics classes. And we can see here, this is going into that. This is from burning energy in this case. But we have, of course, the same similar phenomena in the city. So this one, all of these cars are actually burning petroleum and releasing heat directly, each one of them. Or all these machines here in the factory do the same. Our screen is doing the same, our lamp is doing the same. These refineries definitely are doing the same, and the lighting, of course, is also doing the same. So the work results as well into ambient heat, and we can see that with this part of the firmware. The work is going also into the ambient heat. So W is the work done by the system, energy exiting the system as work, and Q is the heat put into the system, heat energy entering the system. This is these big charts that you saw before. To understand this better and why this is related to design, it's always interesting to see how physics or these other disciplines influence design and vice versa. I don't want to bug you with this. All these slides will be on your website after the class. But this is translating annual energy demand into heat flux, because this is what's interesting us. Energy is something that comes in containers, in pipelines, in ships, in who knows what. We are interested what enters the system of the city and where. So this is why we need the heat flux. In a conservative guess what the energy demand would be of Singapore, we showed before, is this 531,000 terajoule. So that gives us a heat flux of about 24 watts per square meter for the entire island. Versus, if you look at it from another side, of million tons of oil equivalent, for example here, which is the official numbers, it would be 32 million tons of oil equivalent entering into the island. That would give us a much higher heat flux of about 61 watt per square meter. You can see already in a country it's very hard to exactly measure the energy or the amount of fuel that's going in and out, because it's part of a bigger system. But somewhere between these 24 and 61 will be the heat flux in Singapore. We have different countries in the world, of course much bigger countries, but there you can see very different energy density. For example, Mongolia, huge country, very few people, very few factories and so on, would have an artificially made energy density of 0.0027, or Switzerland of 0.866, or Bahrain, which is quite heavy in terms of energy production and heat output, is 16. And Singapore, very high, 24 to 61. There you can see already big differences. So this is the million tons of oil equivalent, and the other one is the terajoule that I showed you before. This leads to the so-called urban heat island effect that we talked about. And the background to this is the global energy balance. Don't want to focus on that either. You can look that up, but this is quite good representation. You have all the incoming solar radiation of a certain amount. Much of it is reflected by the clouds and so on. Others going to the ground, reflected up again. Lots of it is absorbed on the one hand. On the other hand, we have outgoing long-wave radiation that is going out from the Earth. Some of it is reflected back from the clouds back to the Earth. And the total overall net absorbed energy of the Earth is about 0.9 watt per square meters, where some people argue this number is not undebated. Many people argue it's more or it's less. And that is the number that finally will contribute or not contribute to global warming. But it is a fact, since many years known, that we have this so-called heat island effect. And this goes back to the 60s. Who knows what it is, the heat island effect? Or who has experienced it so far? Anyone from New York? No? Chicago? No? Providence, Rhode Island? No?
Toronto?
Toronto, yes, Toronto. It's the same picture everywhere. Outside, the rural world, there, temperature at a certain level. Then you have so-called cliff. This is where the city starts. Although today with urban sprawl, it's hard to see where it starts. Then it goes in a certain plateau, and then you come to the peak. And the peak is mostly in the so-called CBD, the Central Business District. And in there, it's quite hot. And then on the other side of the city, it goes down again. So this is, of course, a planning issue. If you decide to have concentrations of buildings, of people, of density in a city, you create a peak in terms of heat, no matter where you are, because you always put, by design, lots of density into this, and density creates energy, used energy, and creates heat. Here's an example, Providence, Rhode Island, how that looks like. Different temperature measures from satellites. Here you can see the brightness temperature. You compare that here with the built-up land, and you can see clear visual relations between that. And you can see the vegetation. There's a negative relation between vegetation and density and heat. So that seems to make sense, right? But it's not that simple. So in the old days, we thought there was a simple relation, causality between insolation, the energy coming from the sun, and the climate as a natural cause, and that would cause the heat island effect because the sun would just warm up the buildings and the heat would stay longer in the buildings, and therefore it would create this heat island effect. And we look at the energy density that we showed before of whole countries, now in urban areas and city centers. And there we see, for example, Chicago, Cincinnati, they're all pretty high. Manhattan is, since always, a very high one, between 117 and 159. And Vancouver is the only Canadians, and Montreal is also there, 99. So the cities are have a quite high energy density where they are situated. Coming back to Singapore, we can observe the same thing in Singapore. Now you see the map, and now you see the result of urban planning. This one here, as you said before correctly, is a park. But the park was enhanced, if you want, with a large body of water, because this park, the Central Park, is now also a water reservoir that can dampen the ups and downs of temperature. So this is a very stable area. This part is the last remaining big wooded area, and you can see it's a drop of 4 to 5% from the rest of the island. This is downtown, and this is the big airport. And here on the western side, these are all industrial areas and some residential areas here. The old way of looking at this was measuring temperature, surface temperature from satellites, as you see on the left side here. And we see here the airport. This is the downtown area. And we see here the industrial areas. So from this picture, you could not say what is what. And you would think the airport is the worst contributor. But it is actually not, because the airport is only hot during the day when the sun is burning on the tarmac, but in the end, in the night, it can release the energy much better than any energy or heat which is stuck between the buildings in the downtown area. And these are all things you have to know before you start to design, if you want to influence them in a positive way. Here you see a map of the very early planning forest to remain in the center. Rural areas around it have been replaced now by buildings as well. And this here, the city and the urban area and the airport. So that was a planning decision 30 years, 40 years, 50 years ago. And the planning decision directly translates into temperature measurements. So this is the effect of what we do. Here, this is this excursion to the airport. You can see those huge fields that are concrete. And of course, they heat up very much during the day, but they release the heat much better in the night than the built-up areas in the city. And if you think that this airport is now serving more than 55 million people a year on a total population of 5 million, and that they want to increase that to 150 million people, you can imagine what kind of heat will just be released from planes landing and starting in this area. Then the infrared radiation, this is getting a bit too long, but the important point here you should remember that is a difference between air temperature and heat, and there's a difference between heat and heat flux. What we are really looking at is this situation here, and if you take just the surface temperature of somebody's, this is Matthias Berger, you can see he has a hot head, but this is just the surface temperature, but we are really interested in the heat flux, how it feels, and the heat flux is the combination. We can also see that people are very sensitive towards small changes of temperature when it gets very hot, in hot climates. Here, for example, the electricity consumption in Singapore is very, very strongly influenced by the temperature. Although the mean temperature of the month only goes up and down by maybe 1.5 degrees. Imagine here, you have 10 or more degrees going up and down. The air conditioning load that is caused by that is going up and down 10%. So altogether 20% up and down of air conditioning load only based on 1 degree outside temperature change. That means at high temperature, people are very sensitive towards changes in temperature. This is also something you have to know for design. And if we had to look at the heat island effect before and looked at the cities, how they perform, now we also have to look what happens in the cities. And this is your job, again, your designer's job. You take one case study, typical housing project here, and it looks quite innocent if you look at it in plan. You have those HDB flats. You can see what the site plan is, different size rooms and so on. You have a nice mix of proposed park. You have car parks, multi-story car parks. You have supermarkets, so different functions mixed together, and so on. And this is the so-called artist's view of this development. But it looks quite green and quite nice. And in reality, it's like that. And which is also quite normal for this part of the world. It's high density, but it has certain features that should jump into your eyes right away. For example, if you look at these things here, can you see what they are?
Balconies.
Balconies, yeah, but can you see what is on these balconies? Probably not from that far. Yes, air conditioners. So every balcony has their own air conditioner to serve just the apartment behind, which normally they don't have to, but they can turn it on and off. But what happens is, of course, you heard that from Marcel Brüdisau in one of the early lectures, the heat released from one goes to the next, goes up, 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 and at the top it's incredibly hot air that has to be cooled down. And so you have a very, very high electricity bill up there versus lower ones down there. But this is not what we're looking at here. Here we're looking at the insolation, the incoming sun in different places. Berlin, Munich, Singapore, Rome, Addis Abeba. And you can see Singapore is somewhere in between. It's about 170 or something watts per square meter. And then we have the release per square meter of these different building types. And if you look at this building that we just had before, per square meter, we can see that per square meter, this building is releasing more energy than the incoming sun. So you have in this building almost 2 suns shining at the same time. Of course, there are many, many, many floors, and the ground floor, you could say this is unrealistic because it's just a few square meters on the ground. But you have to consider the total energy being used, released in this building. These are the lights, these are the elevators, these are the refrigerators, the washing machines, everything. So these buildings are almost like heating rods, literally standing in the environment, heating up the environment. And that's what they do. They do it at the same magnitude as, for example, the sun. This building here and the whole campus is doing the same thing, but on a much smaller scale. Buildings, we have to consider buildings almost as heat exchangers. Definitely here in these cold climates, but even more so in these hot climates. And there's a phenomenon in nature for that, very unkind one. Do you know this one? What happens there? It's a poor hornet that's been had tried to penetrate into a bee's terrain, and it's killed by the bees just by them enclosing the hornet and vibrating very fast with their wings, creating a lot of heat, and this just melts down the hornet in the center. So this is something we don't want to achieve in our cities, but as a matter of fact, we do something quite similar to that. So we have to leave the old view of just causality from sun and climate and heat island effect, and we have nothing to do with it, to this new one, which is the sun and climate. Yes, very important, but this anthropogenic cultural course, planning course, is part of this effect. Okay, so now we try to model this and to put this into a system that we can model it, predict it, and improve it. These are the different parts. You will find them in the lecture notes. And we look very carefully at the details. This might explain why there is so much noise, even in the upper floors. They think they put the streets here, and they put trees, and then there is no noise. This is not true at all. Unfortunately, the noise propagates even more. But you don't know that until you really live in this environment. So this is the autobahn in the city, which we don't have here in unprotected ways. And each one of these cars is a heat engine running through the city. So that releases the heat continuously through the entire city. It's like you have a heat pipeline in a very hot environment already. And this is, of course, a planning decision, where you put the streets, where you put which streets, and what kind of vehicles you allow on those. One alternative now being detected from this problem, that you see the problem, there's lots of heat, we have to do something, would be, of course, to go to battery cars. Because with battery cars, you would release the heat not when you drive, but before, when you have to load the battery, when you have to generate the energy to load the battery. So that would help a lot in Singapore, but how to replace 800,000 cars with battery cars? So that would be one way, and together with MIT, we calculated that this alone would already possibly decrease the temperature in Singapore on the entire island by more than 1 degree. And that, of course, would result in much less need for air conditioning. And that, in result, would cause then less need for air conditioning in the cars. because our colleagues from Munich, they calculated that alone the energy needed to run the air conditioning in a hot climate like Singapore is enough to power one of their new electric vehicles. So there is so much energy going into just moving the air out into, to be taken into the next car, that you could run the whole car with it if you don't need air conditioning. And so on. Then there are many ways to compute that. It's not understood, these phenomena today. This is where research has to come in. How do actually these cars release their heat? Is it just to the top, or is it to the floor, to the street, and then to the side, and then through radiation to the buildings? It's not really known in detail. Is there a circulation going on, and when is it going on? During the day, during the night? How is that impacting the climate, the local climate? Because that would explain why we have these sudden downpours, this incredible release of hot air boiling up every afternoon. Now you can see these kind of cloud formations. That makes it impossible to predict the weather in that city. Therefore, if you look at the weather prediction of these cities, you see rain all the time. It's not all the time rain, it's just unpredictable when it will come. It could be that it's related to that. But that, as I said, is part of research and not completely found out yet. So with this, I think I want to close, because I hope you see the relation now between energy and planning decision and design. Depending what kind of transportation system you propose, depending on where you propose what on an island, and most important, if you propose to have very separated living, working, leisure, airport locations, of course you generate a lot of traffic by design. And if you know that, then you also know a way to reduce traffic, heat, noise, and I hope you keep that in your mind. Study this very carefully with the exercise that we have for today, a gentle reminder, as I call it. And the gentle reminder is that you hand in your exercise number 2. Where is it? Gentle reminder, hand in your exercise number 2 for next time. And think about these interrelations between energy, transportation, zoning laws, and design. Okay, thank you very much. See you next Monday. Next Monday I will be in Singapore, and I will try to talk to you through that. And there will be a local anchor, that will be Matthias Standfest, and the two of us together will bring home that message to you next Monday. Thank you.